Hello and a warm welcome here in Nuremberg at our Technology Center. My name is Alexander Henning. Today I would like to introduce you to the topic of GMT35 vibratory finishing. Here in the Technology Center, where automation is a top priority, we can see the Garant Basic Plus, a small parts loading system. Or here we see our colleagues at the Garant turntable, an automation solution with vice handling. But now I want to show you the most interesting part of automation. The GMT35, a vibratory finishing solution mobile, 350 kilos, offering the perfect option for your small parts processing. Vibratory finishing increases the flexibility of your production, put your employees to work on meaningful processes, deburring components, rounding component edges, grinding or complex polishing processes. You can do these processes yourself right on site, or if you currently send your parts out, you can now do the grinding in-house, right on site. Parts cost money, 30 cents each. Plus packaging, they have to be sent back, checked again, and only then can you continue processing them. You might end up waiting 3 or 4 weeks for your processes. Grind your components with 100% repeatability and 100% quality, whether it's stainless steel, aluminum, plastics, titanium, 3D printed parts, or prototypes. All components that fit into the machine can be processed here. Now, let's take a look at the Garant GMT35, a 3-in-1 solution. It has everything I need for vibratory finishing. Down here, we've integrated our water treatment system in a draw solution. 45 liters of water are held here on the left in the settling tank. The water overflows and is pumped back into the cycle from here. The compound remains in the system for about 100 to 150 operating hours. What else do we have? We have a modern HMI touch display with a manual mode. We have an automatic mode and a programming mode, allowing you to store up to 49 parts by name. How long have they been running? Which grinding media were used to process them? Let's move on to the heart of the system. That's the steel trough. With a capacity of 35 liters, it sits on 4 springs. The motor is attached underneath and creates the imbalance needed to move the grinding media. It looks like this. Here you can clearly see how the granulate is nicely pulled through the trough. If I want to take out the small parts now, of course I don't do that by hand. For that, we have an additional separation unit mounted here, which is attached to the side. We open it here, can open the trough to the side. The grinding media trickle out into the lower box, and the parts can be collected back here. So, all the components I need for a vibratory finishing system are included here in this mobile solution. Now, I'd like to start by talking to you about the process media, the so-called compounds. I simply need these for small parts processing, for the grinding process. The uni-compound consists of so-called fatty acids, which are made from seed kernels and contain preservatives. This is simply so that the liquid doesn't start to smell and can't go bad. As a rule, the components are ground in the universal compound. We use this one universally here. Here I have another process medium, the so-called shiny. It's a much greasier compound for parts that are supposed to shine, where I know from the start that they are going to be high gloss compacted or polished in the end. Furthermore, we have an aluminum compound. It also contains ammonia for lubricating alloys. Those would start to turn gray in the universal compound. The same applies to copper and brass components. Certain alloys I can process and deburr in the universal compound. There's always some grinding going on. But to achieve a nicer surface on brass and copper parts, I should also use the appropriate compound here. Furthermore, we also have a compound specifically for use with plastic parts. Especially when I have 3D printed dark blue or black parts, they would also get contaminated in the universal compound with residues from the metals. For that reason, it always makes sense to process plastic parts with the plastic compound. Then sometimes I also have really greasy and oily parts after hardening, or parts with scale layers that I want to remove. I can also do that here in the system. For this, we use what's called clean. That's a washing powder, which is also added in. It has a very strong, aggressive cleaning performance, and with it I clean all my greasy and oily components. The compounds are added to the process water at a concentration of 3 to 5%. They remain in the system for between 100 and 150 operating hours. An aluminum, compound aluminum parts, as you can imagine, turn black very quickly. I have a lot of contamination in my process water, so sometimes I change it after just 100 hours. With stainless steel, it can run for 150 to 160 hours. The water is then disposed of together with the cooling lubricants from the machining machines. You can find data sheets online or just ask your local municipality again. Depending on the district, there are also different options for disposing of the materials. So let's take a look at the mystery of grinding media. Out there are about 2,000 different types of grinding media. We somehow decided on 28 for our system, which work best in it and allow us to cover 95% of all components. To shed a little light on this abrasive or grinding media topic, there are actually only 3 categories that are relevant for us. The first would be a ceramic. If you take a look at the grinding media under magnification, you'll see a lot of black spots on it at first. These are chip spaces, pore spaces. The structure is very porous. It's a ceramic pressed together with aluminum oxide. They are then baked together. And the aluminum oxide forms the grain tips, which, as you can see very clearly in the second image, are embedded in the ceramic. This grain tip, is there for grinding because only this aluminum oxide grain tip can remove a burr. That's what I need it for. If I had only pure ceramic, I would just bend the burr over. To prevent that, I simply need the abrasive grain that is built into these grinding grains. Then we have these different geometries. Take a look at this. Yes, 3 by 5 millimeters or 6 by 6 millimeters, 10 by 10 millimeters. So you can see that as well. That's always the geometric size that we see here at the back. And it's simply so that the grinding body fits my component. If I have a small component where I want to deburr the inside, of course, I'll go in there with the 3 by 5. If I have a laser cut component, something large with a lot of scale on it, then of course I'll use a large grinding body like this. These are suitable for all hard materials. I can also use them to work very well on high alloy aluminum. But then there are also these lubricating alloys, brass, copper. With those, it's already difficult to work with a ceramic like this. For that reason, there are also plastic grinding bodies for these materials. And these are simply grinding bodies that are pressed from plastic. They also have a lot of pore space built in, as you can see in the first picture. And in the second picture, you can again see these white dots. The aluminum oxide that is built in here forms the grain tips. I need those for grinding. The plastic is lighter, softer, and more flexible than a stone or a pressed sintered ceramic. And these are ideally suited for working on plastic components. We also have them in different shapes again, right? Sharp points, which are a bit more aggressive, or these rounded cones. With a nice little triangle like this, I can, of course, get into all the corners of components. It also fits nicely into a hole, can rotate smoothly inside it and deburr it. Once I've finished grinding the components, they are usually anodized, painted, or simply assembled and screwed together. However, some components are also visible parts, and then I say, oh, now I have this grinding mark on the surface and I'd rather get rid of it. For that, we still have the option here to use our 3 ceramics to achieve a high gloss finish. It's a pressing process, so no more grinding. Of course, beforehand, I have to make sure the components are finely ground, remove milling marks, round off the edges, and then, depending on the component and material, I can densify the surface here in about 2 hours to create beautiful high gloss pressed surfaces. These are the 3 grinding media we work with. The different geometries ensure a proper fit. Do I need something round or do I need something angular because I have a groove and want to grind the bottom of the groove cleanly? Then I simply have the choice here. And it's also the case that if I have a problem with ceramics, even on hard materials, if I don't have access or the grinding medium is too aggressive, I can of course also work on stainless steel or steel with one of these plastic tools because they contain aluminum oxide, those abrasive grains, and they do the grinding. Yes, let's talk about the topic of process accuracy or repeatability in the machining of components. The colleagues in Munich once measured a component before and after machining and did so with 2 different grinding tools. Here I have the 15 by 30, the large one, and the 5 by 10, the small one. Let's take a look at this slide on process parameters regarding the topic of edge rounding. At the bottom, the scale shows us the time. On the left of the bar, I can clearly see my measurement And then you can clearly see that after 1 hour, I have 100 of edge rounding. After 2 hours, with the large grinding tool, I'm at 0.5, and with the small one, 0.3. So you can clearly see that over the processing time, the edge rounding increases as well, always depending on my material, whether it's steel, stainless steel, or aluminum. That's obvious. Parts made of aluminum, for example, are already processed to a certain degree after just 15 minutes. With stainless steel, I might be working on it for 20 or 30 minutes. Next, let's take a look at the surface roughness. You can also see this very clearly again in the second row. The roughness RZ changes over the time axis. Yes, it becomes noticeably finer here. Of course, the small grinding body is very obvious here. It creates a much smaller, finer surface. If you imagine it, when I grind, everything that stands out in the measurement gets ground down and planed together by the grinding body. Of course, the larger one leaves a rougher track than the smaller one. You can also see this very clearly in the surface roughness RA here on the slide. Now I'd like to talk with you about the topic of component processing. Which grinding body do I use for which component? And how do I choose the best one? Here we have a nice sample case with various components, different materials, where you can see before and after how they have been processed. For example, let's take a look at an aluminum part here, a 7075. It's a turned part, a damper or a flute. Here you can clearly see the turning marks on it. It's very difficult to deburr on the inside. And then I consider which grinding body would be a good fit for this. In this case, the small cylinders would of course be very suitable. They can move through there nicely. Here, there's almost a risk that it could get stuck. In this case, we decided on the 3x5. Right, it's this size, it can go in nicely, it removes the burrs inside, it can move sideways into the holes, and it works wonderfully there. It ran for 3/4 of an hour with that grinding body, the milling marks are gone, and you can basically send the part off for anodizing, coating, or painting. Here you can clearly see the before and after. The turning marks are gone, the surface is nicely matte, and I have the ideal conditions here to coat the part. Natural anodizing or powder coating. If, of course, I don't like that and I want the surface to be shiny, as we've said or discussed, we can also polish it to a high gloss. Here we ran it through the porcelain again for an hour to really compress the component to a beautiful high gloss. A very nice result. I can process 3 components per side in the trough at the same time, even when I'm polishing them. So I have a total of 6 components in the system, which are all completely finished in 3 hours. What else do we have? I've also brought you a laser cut component. This is something you see very often, like welded parts. You can clearly see the discoloration on the edge here, and it's extremely sharp edged. You just run it through the medium abrasive media for 45 minutes. Oh, and here I can easily get into all the inner areas as well. It goes nicely through the hole and can also easily remove the burr on the hole. After an hour of processing, if there's a heavy burr, I just let it run for an hour and a half. Then I simply have a clean component that can be further processed, welded, painted, or machined. That's that. What else did I bring for you? Here we have a printed steel ball. Especially 3D printing is, well, becoming popular everywhere. And here you can see a ball like this, yes, printed from steel, from structural steel. Down here we cut it off. It was rounded off a bit by hand, and then we simply ran it for 2 hours in the big 15x30, just so you can really plane down these printing structures nicely here. Yes. After the runtime, you can polish structural steel or anything that's easy to machine. It also polishes well. And this is what it looks like. We then just run it for another hour in our smallest porcelain, and you can see here a beautifully pressed mirror finish. Right, it looks very nice. So no one has to work on this by hand for a long time. You just let it run so that the parts have a nice polished surface, are deburred, or the edges of the components are rounded. The whole thing also works very well with plastic. POM, for example. Here we have one that always has very sharp edges. When I deburr it with a blade, I always ruin the edge. That really doesn't look nice, and everyone uses these parts somewhere. These are holders, spacers, almost everyone has them in their lineup. So we just run this one through this triangular plastic as well. Here I can simply let it work in the holes again. It removes the burr everywhere. Yes, it's a kind of semi-aggressive abrasive body. And here we can already see this is a very hard plastic. In that case, I use a ceramic. Then I don't necessarily have to rely on the plastic abrasive bodies. It's a different story if I have 3D printed plastic parts here in various colors. Here you can see it nicely printed. You can see the layer lines on it. And to remove those layer lines a bit, to get an initial feel for the part, you can process them very well with a plastic abrasive body. The advantage is, with this ceramic, you can imagine it's a ceramic, it wears down. I end up with this white residue, this ceramic sludge on my part. Especially if the part is dark blue or black, I have to work with the plastic compound, with the plastic abrasive body, so that I don't get these contaminants on my part. Those are the options I have to flexibly respond to my parts and see where I need to go. Rough preliminary work, laser cutting, removing the edge, the surface, removing milling marks. For that, of course, I use something larger. If you take a look at a triangle like this, you see it also has a large surface area it can work with. In contrast to a cylinderic that's lying flat, there's significantly less abrasive grain at work. And that's how I always look at it, what's important to me, where do I want to go with the component. So that's about it on the topic of vibratory finishing and the GMT 35 here from Nuremberg. I hope I was able to answer a few of your questions. For further information, please contact your regional sales manager. You can also find more information on our website. I wish you all a wonderful day. I'm going to keep grinding a bit more and I'll see you around. Bye.